So 7.2, confidence intervals for the mean. And I'm going to write out instructions as we go. So let's look at the first question here. So, you can't see it very well, huh? So first question, so refer to the accompanying data display. So here's an output that results from a sample of airport data speeds in MPBS. What is that? Megabytes per second. The results in the screen display are based on a 95% confidence level. Write a statement that correctly interprets the confidence level. No. So basically, they're going to start, we're just going to read and answer. I think this is the only one. No, maybe there's a couple of them. Then the rest will do it. So let me write it bigger for you. So 13.046, comma 22.15. What does that mean? What is that saying? That's the 95% confidence interval for airport data speeds. So what are we saying when we say that's a 95% confidence? By the way, see how that's average numbers, not percentages now? I mean, we always have this as a percentage. But I mean, that's the average data speed. That's the range of average data speeds at an airport. So what we're saying is that we're 95% confident, sure, that the true, remember it's always about getting to the truth, that the true average airport data speed is somewhere between 13 and 22 megabytes per second. Does that make sense? So you get an idea of what we're doing with these confidence intervals? Remember, we're always trying to get at the truth. There is some true average. There's some true average out there, right? Of what the true average speed at all airports in the world. If you took every airport in the world, somehow if you could do that much thorough work, if you took every airport in the world and you took all their, high-speed data speeds, you added them all up and you averaged them, there would be some real average that exists for all the airports in the world. We don't know what it is. That's too hard to do all that work. So what do we do instead? We take a sample. We go to 50 airports or 30 airports, and we take their speeds. We figure out their average. See the X bar right there? That's the average they got. The X bar. So they went to a bunch of airports. In fact, how many airports did they go to? Yeah, 50. They went, in is always the total number, huh? They went to 50 airports, took down all their data speeds, added them up and found the average to be 17.598 megabytes per second. That's the average data speed at the 50 airports they sampled. But that's not every airport in the world, is it? That's not every airport in the world. And what we want to know, suppose they want to write an article or a paper about the average data speed for all airports in the world. What's the true average at all airports in the world? How are they going to do that? Well, can they say, we're confident it's 17.598? No. That's just the average for the 50 airports they looked at. How about the whole rest of the world? Well, that's why we form confidence intervals. We can become 95% confident that the real average, the true average, is around this 17.598. It's below it by 4 or above it by about 4. See how that 13 and 22 are about, subtract 4, add 4. 17 is right in the middle. 17.6 is right in the middle of 13 and 22. It always is. The average is always right in the middle of the confidence interval. You take your confidence interval and you add and subtract the error margin. That's what we mean by the error margin. So we're saying, yeah, we're 95% sure, confident, that the real average data speed for all airports in the whole world is somewhere between 13 and 22 megabytes per second. That's what we're saying. Is this making sense? That's way more important than all these moving numbers around. You will likely never move the numbers around in an actual statistical thing in your life, but you will read a confidence interval study, very likely. And you want to know what that means. That's the main thing of any benefit to you in this class, is really knowing how to read a statistical report when we're done, and what those things really mean. So is that making sense then? That's really the most important thing. What that actually says. So which one of these is right, A, B, C, or D? C. C? we have 95% confidence that the limits of 13 to 22 contain the true value of the mean of the population of all data speeds at the airports. Yeah, that's it. We're 95% confident that the true average is in there. Because that's what you always want to get at, right? The truth. Just like when they poll before an election, right? They say we talked to a bunch of people and 55% are going to vote for candidate A. But they're not sure that's what's going to really happen for the whole nation on election day. So they form a confidence interval. They might say it's somewhere between 50 and 60, for example. You know, we got 55% in our sample, but maybe we're 99% sure that the whole nation's going to be between 50 and 60%. That's what they do. All right, you're good with that. Let's move on. Okay, so here's some summary stats. Randomly selected weights of newborn girls. Number of girls, average, standard deviation. Construct a confidence interval estimate of the mean. Use the 90% confidence. So are these results very different? Okay, so here we're going to actually do one. Okay, so I'll tell you how to do it then. So let me write it a little bigger for you. Over here. What were the numbers? It was N is 192, X bar is 33.2. N is 192, X bar, I already forgot, is 33.2. And, okay, and S is 7.3. And they want a what? 98%, okay. So 98% confidence interval. All right, does everybody understand what's going on? We got a bunch of newborn girls, 192 newborn baby girls, and we want to figure out, hey, what's the true average weight for all newborn baby girls? So we got an average of 33.2. I don't even know what that is. Grams? What that is? HG. What's HG? What is it? It's weird. HG. They're all HG. I know. Is it hectograms? Must be whatever.
Kilograms. A lot of kilograms.
All right. So it's 33.2 something. That's the average girl's weight that was born in our sample of 192 girls. But we want it, but again, that's just for our sample. We want to know all girls, right? That's always the goal. Find the truth that's out there. What's the average weight for all newborn baby girls? Well, we don't know. Let's form a 98% confidence interval. All right, so we're going to do this on our calculator. It's very similar to what we did last time. Let me write out for you the steps. So you hit the stat button, go over to the tests, and go down to, on my calculator, it's number 8. Might not be number 8, probably is number 8 on yours. T interval. So go down to T interval, hit enter. Y'all finding that on your TI calculator? T interval. And then what you'll get is you'll get this screen which says, how do you want to input the data? It's asking you first off. Do you want to do it by a data set or do you want to do it by stats? You want to highlight the stats by pushing enter over the stats. Maybe it's already highlighted. Hit enter on the stats button. I'll explain what that means in a minute. We'll do both tonight, so we'll do both data and stats. Hit stats, and then next it's going to ask you for X bar, and it's going to ask you for S sub X, and it's going to ask you for N, and the sea level. So X bar, 33.2. S sub X is this standard deviation for the sample, 7.3. N is 192. It's as easy as that. The sea level is the 0.98. And then just hit enter and your calculator will do the magic. And I got the following answer. I got 31.964 to 34.436. Y'all getting that? On the calculator, so let me pause a question, which I don't always know the answers to these questions. Then they say, okay, what did we get? We got 31.96, 34, so 31.96 to 34.43. And then they said, hey, if we just did 15 sample values instead of 192, we got this interval. How's that compare? It's pretty similar. 31, 31, 35.7, 34.43. It's about the same thing. Very, very similar. Are the results very different? No. No, because each contains the mean. No, that's actually not the reason. It's because the confidence intervals are similar. Yeah, I see it now, why they would want to say that. Why would they not want to say that each contains the mean of the other? You probably, I know you're just new to it doesn't make a lot of sense right now.
That error?
Of course they contain, that's like a silly thing for them to say. Of course they contain the mean. You start with the mean for any confidence interval. So this mean is going to be the middle of any confidence interval. Of course they do that. That's saying nothing. Right? You start with the middle. It's just how wide you go from the middle is the confidence interval. And so this and this are about the same width. So that's why it's not the mean. Anyway, I'm not going to test you on that particular kind of fine point. Clinical trial was conducted to test the effectiveness of a drug for treating insomnia in older subjects. Before treatment, 16 subjects had a mean wake time of 101.1 minutes. So they were awake, during the night of 101.1 minutes. So that's too bad. It's a lot of wake time. After treatment, that's that's almost 2 hours, huh? After treatment, the 16 subjects had a mean wake time of 77.8. So after they took the treatment, the drug, their wake time went down, didn't it? They were still awake more than an hour, 77 minutes, but that's lower. And a standard deviation of 21.6 minutes. Assume that the 16 sample values, so the 16 subjects, 16 sample values appear to be from a normally distributed population. Yeah, all of this has to be from a normal population, like usual, because all these things are based on a normal curve. And construct a 95% confidence interval estimate of the mean wake time for a population with drug treatments. All right, so, in other words, let me make sure the big idea is making sense. So, for these people with no drug or before the treatment, their wake time, they were awake on average, X bar, 101.0 minutes. So that they were almost 2 hours awake every night before they took the drug. And then after the insomnia drug, their wake time average went down to 77.8 minutes. And that's 16 people, right? That's N equals 16 people were given the drug, and it went down. Now, so should we believe, here's the question, should we believe that drug is really making a difference? I mean, that's the important question, right? If you're going to mass market this drug, or if you have insomnia and you're interested in whether the thing really works or not, you would want to know some statistical evidence that it's really reliable. Well, how do you statistically determine if this drug is really making a difference? Now, you might think, what do you mean? Of course it is. The average went down. What's my problem? Why do I keep asking that when it clearly went down? Why is there even a question that remains? Well, yeah, I mean, give me some real. Like, what if somebody off the street? Don't give me statistics lingo. Just be real with me. What if somebody off the street said, hey, what are you doing all this stuff for? This is dumb. Here, let me play Joe Blow off the street, because that's who you want to communicate to in the end, right? You write a report, you speak to a boss or a co-worker with statistical information. That's what we're doing here, right? I mean, there are people that do this. My son just got a job doing kind of like this with Excel. I mean, these are people that do this. I mean, 2 months ago, he graduated with his math degree, and he got a job. He got hired in Fresno. He basically looks at Excel spreadsheets all day long and helps the company figure out where they can trim costs and what they should do number-wise. He helps them see which products are making money, which products are not. He runs all the numbers. So he has to go into the boss's office. They call him into meetings all the time. He has to take these Excel spreadsheets and he has to bring it down into layman's terms. They don't all have math degrees, but they know he does. And so he sits down with them and says, okay, see these numbers here? This means this product is making us money, but this other product is not because we need to start charging sales. And he recommends things. So how would you bring this down to basic level? Like what if a person came up to you, your colleague, you're trying to present, and go, what? Says, what are you doing all this stat stuff for? Of course this drug is working. Look, the average wait time went down. I don't need to take a statistics class to see that. Of course it's working. What would you say?
But it's only for this question is 16 subjects, so it needs to be
Well said.
More. Like
Yeah.
People would have a more accurate
Yeah.
measurement.
Yeah. This is only for 16 people. Yeah. So what could be the problem with 16 people?
It's too small.
Yeah. Those could be weird 16 people. I mean, that's possible, right? They could just be 16 people who, maybe, I don't know what, something else happened in their life that next week, and so they slept better. I mean, it could be, right? There's randomness in life. Now, if you say, no, that couldn't be, well, no, that couldn't be, isn't very convincing, right? That wouldn't convince your boss. That wouldn't convince an important group that you're trying to persuade that the drug really works. That won't convince the consumer market. We need something more than, oh, no, it probably wasn't luck. Well, give me some hard, fast numbers. How do you know it wasn't luck? How sure are you it wasn't luck? That's what we're doing here. Does this make sense? So we're going to form a 95% confidence interval. We're going to say, yeah, that was the average for this group of 16 people. But the real average for everybody who takes this drug might not be this. What might it be? We'll get a confidence interval around that. Does that make sense? We want to become 95% confident of what the real average of everybody who will ever take this drug. What is this drug really going to do on the average? That's always what we're going for, is the real truth. Right? That's always the game, right? So, all right, so if we have this average, 77.8 for that little sample of 16, let's form a 95% confidence interval for what the true average for everybody who will ever take the drug is. So let's go to our calculator. Let me bring the data over here. X bar was what? 77.8. 77.8 minutes. Do we have an S? Wasn't there an S somewhere? Oh, there it is. Standard deviation 21.6. So we always need that. 21.6 in 16 people. And the confidence interval 0.95. So go to your calculator. Hit the buttons. I'll do it too. 66.29. Let me get it here. What's stat? Test. So it's the same thing as last time, basically. Wait, I'm in the wrong one. Yeah. So I'm getting, 66.29 to 89.31. Okay, so now that's my 95% confidence. Okay, now let's be real with this thing, because that's the real use of this class. What does that really mean? What does that really mean? And to bring that in, let's say, what was the average before the drug? There it is, 101. Okay, so what does that 66.29, 89.31 really mean? What would you say to the person that says, So how do we know how sure we are that the drug's working? Can we be confident the drug really is working? Or maybe those people were just luckily sleeping. Is there a chance of that? Is there a chance it was just luck? What do you think? I'm not putting you to sleep right now, am I?
Isn't it no because the meme's not included in the first
Well,
one?
let's start off with what does this really mean?
That's the range of 95%.
Yeah, we are 95% sure, confident. We are 95% confident about what? That the real effect of this drug on people who take it, who have insomnia like those other people did, right? It's people, you know, right? Remember this people had 101 minutes of insomnia on average. That the true average effect of the drug will be to make your insomnia go somewhere between 66 minutes and 89 minutes. We're 95% sure that if before your insomnia had been what? 101? If before your insomnia had been 101 minutes, right, that was the average for our group before. So if you're one of those kind of people who has a 101-minute insomnia beforehand, we are 95% sure that if you take this drug, it'll bring your insomnia level down to between 66 and 89. So, and that's confident, isn't it? Is there still a chance it could be luck? Yeah, but it's less than 5%. There's also a chance you're going to go outside and get hit by lightning twice, but it's not likely, right? So it's all about what's reasonable. In a court of law, this would be evidence beyond a reasonable doubt. This would be strong statistical evidence. We're 95% sure that it reduces the amount of insomnia. Doesn't it? We good there? Does that make sense? 95% sure because it doesn't contain the 101 in there. All right. So let's move on. How we doing? We got 20 minutes. I got to show you one other type and then an in. So I better move on. So you can answer all those other questions. I think they'll be easy for you. A food safety guideline is that the mercury in fish should be below 1 part per million. I guess there's mercury in fish. If you eat too much fish, you can take in too much mercury. Not a problem. I guess it's not good to eat mercury. That's for thermometers, right? And not for human bodies. Listed below are the amounts of mercury found in tuna sushi sampled at different stores in a major city. Construct a 99% confidence interval estimate of the mean amount of mercury in the population. Does it appear that there is too much mercury in tuna sushi? All right, so let me just write those numbers down for you a little bigger. So 0.51, 0.68, 0.10, 0.88, 1.27, 0.59, 0.82. So what we're going to do now, so see the difference between this question and the last couple? They're giving me actual data values. This would be like if you go out, you do a study, you sample some tuna sushi at different stores in a major city like Fresno or whatever, and you get these numbers. This is the amount of mercury. That one's bad, huh? That one's that's over the limit there. So that's the amount of mercury in those various fish, the tuna sushi. So what we're going to do on our calculator is we're going to put these, guess where we're going to put these numbers? L1, our favorite place. That's right. Just put them down L1. And then when you go to the same interval thing we did before, you just choose the data instead of the statistics. And it just does it for you. It does everything. This is actually easier once you've got the L1 in there. So go to stat. So you got to hit, stat and edit. And put that stuff down L1. I'm going to need a little light there. Can you still see okay? Yeah, you don't have to. Just leave it at 1. You don't have to do anything with it. Okay, I got my numbers in. Yeah, so doing okay. So put that in, and then when you go to your then you hit stat and go over to tests. Again, down to number 8, which is T interval. Again, same test. Like usual.
Number 8.
Yeah, number 8, just like same thing as we've been doing. But this time, you're going to choose data instead. So hit enter on data. You're telling it to get all of its numbers from the data set in L1 instead of from summary statistics. We've been entering summaries, right? Averages and standard deviations and things. Now you're going over to data, hitting enter on data, and then list should be L1, frequency 1. So list, it should already have that in there. I don't think you'll need to mess with anything. Frequency is just 1. You'll have to mess with the C level maybe. What are we doing? What level we want? 99. So make the confidence level 0.99 and hit the buttons. And I'm getting the magic numbers 0.18764, comma 1.1981. You getting that?
Yep.
That coming out for you? That's what it spit out for me. So it took all that data and it found a middle, an average, and it made a confidence interval around that middle. So it is telling us, do you know what that means? It is telling us that based on this data, we can be 99% sure, 99% confident, that the real average amount of mercury in sushi, tuna sushi, is somewhere between 0.18 and 1.19, whatever, parts per million. So let's answer the other. So far so good? Anybody need their questions? Does it appear that there is too much mercury in tuna sushi? So before we even read all this stuff, just real life, what do you think? So this is what matters. This is what you will read and interact with most likely. This confidence interval, this 99% confidence interval, what is it saying to you? Is there too much mercury in tuna sushi?
Yeah.
Yeah.
How do you know?
Is the mean can be
Yeah, because it's all about 1, right? Remember, the food safety guidelines said you shouldn't have more than 1, and 1 is in our interval. So there's a chance that the true average, remember, we're going after the truth. Everybody get it? We're always, we're not just, we just used our sample to try to get at the truth, like a poll tries to get at the truth of how the election's really going to go, right? We're trying to find out what's the true average of mercury out there in all tuna sushi. Well, could be more than 1, huh? We're 99% sure the true average is between 0.18 and 1.19. 1's in there. So it could be that the real average is more than 1. Could be. So there's a risk here, right? That kind of study would raise some eyebrows. That would say that there's a chance. So we're not safe, in other words. If 1 was not here, if we'd gotten some kind of interval, if instead we'd gotten some kind of interval like 0.20 to 0.60, 99% confident, then we would say, oh, no, we're very sure that the true average is somewhere between 0.2 and 0.6, so it's certainly less than 1.0, and we're 99% sure that the real average amount is safe. Right? But that's not what happened. 1 was in our interval. Numbers more than 1 were in our interval. So we're not sure the tuna's safe. Is that good? These studies making sense? So I don't know what. So does there appear to be too much mercury? Yes. I don't know if it's B or C. Yes, because it is possible that the mean is greater than 1. Also, at least one of the sample values exceeds 1. So at least some of the fish have 2. Yeah, that looks good to me. What's C say? Yes, it's possible that the mean is not greater than 1. No. B. Yeah, B. It's possible that the true mean, right? Remember, we're always going after the truth. The true mean, we're using our sample to get at the truth. All right. It's saying, basically, if you look here, I'll just give you a real quick fact. Basically, they're saying you survey a bunch of students, teacher evaluations at one university. All those evaluations, numbers, teacher evaluations, come from one university. So then down here they say, what does this confidence level tell us about the population of all college students in the state? Nothing. Because since the sample is only from one university. You see, if you want to know information about like the whole state of California, you can't just ask people at West Hills College, Lemoore, right? You can ask some from here, but also some from down south and some from up. You gotta survey the whole state if you want to make an accurate statement about the whole state. So that's what they're doing wrong there. All that information is from one college. That might be a weird college. You got to ask students from all the different, or at least several colleges spread throughout the state if you want to make a conclusion about the state. If you just want to make a statement about that particular college, great, you can do that. But if you want to make a statement about the whole state, you got to take more data from other colleges. We want to do, again, we're planning to do a study. We need to know how many people to survey. So if you're forming a statistical study, you determine ahead of time how many people you need to talk to get the kind of accuracy you want. IQ test designed so that the mean is 100, standard deviation 12, population of normal adults. Find the sample size necessary to estimate the mean IQ scores of statistics students, such that it can be said with 95% confidence that the sample mean is within 3 IQ points of the true mean. Assume that the sigma is 12, determine the required sample size using technology, determine it's reasonable, blah, 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 blah. All right, so you need another formula. There's a different one. It's easier for the N. There it is. So let me give it to you. So for 7.2, N equals the Z numbers, same Z numbers as before, times the S, standard deviation, over E, the whole thing squared. It's much easier. You don't need two, there's not two versions. Z times S over E, the whole thing squared. Much easier formula. So that's the N formula we use in 7.2 for means. We're talking means now, not percentages, right? Like the average amount of mercury in the tuna sushi, for example. We're talking average amounts, not percentages in this section. So 7.2, number 6, let's do it. So suppose you want to estimate the number. So it's going to be Z times S over E squared. So what is, let's get these numbers. What is Z? We're doing a 95% confidence interval. So for 90, you got to look back to 7.1. I don't want to write all those out again.
6.95.
Yeah, no, I've got them here. But yeah, so for anybody watching the YouTube, I want them to know that look back to the last lecture, 7.1, and there's a table there. 63986. So there's the Z times the S. What's the S?
Standard deviation.
Yeah, what is it? It's that 12. Yeah, does everybody know that sigma is the same thing? 12 all over the air. Well, how much air? We want to get the average IQ within how many points? 3, right? We want to be accurate. We want to figure out the average IQ within 3 points. And then take all of that squared. I put a bracket around it. Brackets are the same thing as parentheses. Doesn't matter. Same thing. Just hit the buttons. Square it at the end. 61.46. Are we getting that?
Yep.
And what do we always do with end numbers?
Round up.
Round up. We always want to talk to more people. Right? Talking to more people is always more accuracy. You can't talk to 61 and a half people. And if you talk to only 51 people, you did less than you needed. So you gotta talk to 62 people to get the accuracy you need. Let's make sure this number to it. So n is 62, and then what do they ask down here? Would it be reasonable to sample the numbers? Is that reasonable? Can you talk to 62 people?
Yeah.
Yeah, that's not a hard number. It's a fairly small number. Or wait, not no. Would it be reasonable? I should say yes. Yes, this is a fairly small number. Yes, you can talk to, if it came out 240,000 like the next problem will, that's not reasonable. You're not going to, you better give up some accuracy if you need to talk 240,000 people. Is that making sense? 7 and 8 are the same thing. Just use that same n formula, which is easier than the other n formula.